understanding multiple regression, and why it exists. When people try to explain outcomes in markets or business, they often rely on a single explanation. Interest rates moved, earnings changed, sentiment shifted, but real outcomes are rarely driven by just one force. Multiple regression exists because reality is layered. Prices, returns, and valuations respond to many influences at the same time. Instead of blaming one variable, multiple regression allows us to examine how several factors contribute simultaneously to a single result. The goal is not prediction alone. The goal is understanding structure. We want to know which forces matter, how much they matter, and how they interact when everything is moving together. Without this framework, analysis collapses into storytelling, where whichever explanation sounds best wins. At the center of multiple regression is the idea of isolation. Each coefficient measures how the outcome changes when one factor moves, assuming all other factors remain unchanged. That assumption does not describe the real world perfectly, but it creates structure. Without it, comparison becomes impossible. This is where many people go wrong. They read coefficients as unconditional truths, instead of conditional relationships. A coefficient does not say what usually happens. It says what happens under a very specific condition. When interpretation ignores that condition, confidence replaces understanding. Regression simplifies reality so that disciplined comparison becomes possible, not so that certainty can be claimed. Adding more variables does not automatically improve a model. When explanatory variables are related to each other, they share information. The model must decide how to divide their shared influence. Remove one variable, and the others absorb its effect. Add it back, and estimates shift again. This sensitivity is not a flaw in the math. It reflects overlap in reality. Good modeling is not about including everything that moves. It is about choosing variables that belong together conceptually. Mathematics cannot fix poor reasoning. Statistical significance alone is not enough either. A result can be statistically strong and practically meaningless. What matters is whether the size of an effect changes decisions in the real world. Finally, regression does not establish cause. Two variables can move together because they share a trend, respond to a hidden driver, or simply coincide. Strong statistics do not prove explanation. Causal interpretation requires logic, timing, and reasoning beyond the model. Regression supports thinking, but it does not replace it. Used correctly, it helps us understand complex systems without oversimplifying them. Used carelessly, it creates confidence without insight. The difference lies entirely in interpretation. time trends, and why data can lie. Some data behaves differently simply because it unfolds over time. What happened yesterday often influences what happens today. Prices, interest rates, spreads, and economic indicators rarely reset independently from one period to the next. This creates dependence. Observations are connected, not isolated. Many standard analytical tools assume independence. And when that assumption fails, results become misleading. Ignoring time dependence creates false confidence. Relationships appear stronger than they really are. Understanding time-based behavior is not about complex math. It is about recognizing that history leaves fingerprints, and those fingerprints shape both outcomes and interpretation. One of the most dangerous consequences of time dependence is the illusion of meaningful relationships. When two variables trend in the same direction, models often detect strong connections even when none exist. The statistics look impressive. Explanatory power appears high. Confidence grows quickly, but the relationship is artificial. It exists because both variables are drifting, not because they influence each other. This is how spurious relationships form. Without addressing trends, regression mistakes share movement for economic connection. The model is not revealing structure. It is rewarding coincidence. To deal with this problem, analysts transform data. Instead of analyzing levels, they analyze changes. Instead of raw values, they focus on growth. The goal is stability. Meaningful inference requires statistical behavior that does not wander endlessly. When averages and variability remain stable, relationships become interpretable. When they do not, results lose grounding. Transformation is not about making data look better. It is about restoring comparability across time so that interpretation becomes honest instead of impressive. Time dependence also reveals whether systems absorb shocks or resist them. Some environments allow disturbances to linger. Others correct quickly. This distinction affects expectations, forecasting, and risk. Persistent systems carry memory. Mean-reverting systems resist deviation. Ignoring this difference leads to flawed assumptions about stability and change. Markets rarely forget instantly. When time matters, analysis must adapt. Otherwise, confidence grows while insight quietly disappears. Why relationships change with context. Many relationships in data are not fixed. They depend on conditions. A factor that matters in one environment may become irrelevant in another. Markets behave differently during stress than during calm. Businesses respond differently during expansion than contraction. Treating relationships as constant oversimplifies reality. Conditional thinking acknowledges that effects can change depending on context. Models that ignore this often appear stable, while quietly misrepresenting behavior. Recognizing conditional structure is not about complexity. It is about realism. Relationships are rarely universal. They are situational. One way context enters analysis is through categorical states. Some conditions are not numerical. They describe regimes, classifications, or environments. Stress versus stability. Growth versus decline. Inclusion of these states allows models to compare behavior across situations. Interpretation always depends on what is excluded. Effects are measured relative to a baseline. Without understanding the reference point, conclusions lose meaning. Context does not add noise. It clarifies comparison. Ignoring it forces models to average behavior that should never be averaged. Other relationships change smoothly rather than abruptly. The impact of one factor may strengthen or weaken as another factor grows. These interactions create dependency. One variable no longer acts alone. Its influence depends on the level of something else. Interpreting these models requires care. No single number explains the effect. Meaning emerges only when variables are considered together. Focusing on isolated coefficients in these settings creates confusion. Understanding interaction requires thinking in combinations, not in parts. Context also introduces nonlinearity. Small changes can matter greatly in one range and barely at all in another. Growth behaves differently than levels. Proportional change often communicates more than absolute movement. Transforming variables does not complicate interpretation. It refines it. The choice of structure determines meaning. Models do not discover truth. They express assumptions. Making those assumptions explicit is what separates useful analysis from elegant distortion. Prediction versus understanding. Not all models are built for the same purpose. Some are designed to explain relationships. Others are designed to predict outcomes. These goals sound similar, but they lead to very different choices. Explanatory models prioritize clarity. They focus on structure, assumptions, and interpretation. Predictive models prioritize performance. They care about how well results hold up when new data appears. A model that predicts well may offer little insight into why things happen. A model that explains well may perform poorly out of sample. Confusing these goals leads to misuse. The first step in good modeling is knowing which question you are actually trying to answer. Predictive models are evaluated differently. What matters is not how well they fit the past, but how well they generalize. Strong in-sample performance often means very little. Models can learn noise just as easily as signal. This is overfitting. The model appears brilliant on historical data and fails quietly in the future. The tension between flexibility and stability defines this problem. Simple models miss structure. Complex models chase randomness. Good prediction balances these forces rather than maximizing either one. Performance without discipline is fragile. Because prediction focuses on future performance, evaluation requires separation. Data is divided intentionally. One portion teaches the model. Another helps tune its complexity. A final portion judges performance honestly. Using the same data for all three creates false confidence. The future must remain unseen. This discipline protects against self-deception. It also explains why predictive accuracy should never be trusted without context. Numbers alone do not guarantee robustness. They must survive exposure to uncertainty. This trade-off between explanation and prediction shapes modern analysis. As accuracy improves, interpretability often declines. Complex systems can deliver strong forecasts while obscuring logic. This is not inherently bad, but it demands responsibility. When decisions carry consequences, understanding limits misuse. Prediction supports action. Explanation supports trust. Knowing when each matters is part of judgment, not mathematics. Why complexity must be controlled. As models become more flexible, they become more dangerous. Flexibility allows a model to adapt closely to data, but also allows it to learn patterns that do not persist. This is the cost of complexity. A model that fits everything perfectly is often capturing noise rather than structure. The goal is not to eliminate complexity, but to control it. Without restraint, models become fragile. They perform impressively in hindsight and disappoint quietly in practice. Good modeling accepts imperfection in exchange for durability. One way complexity is controlled is by introducing penalties. These penalties discourage excessive influence from any single factor. Instead of allowing estimates to grow unchecked, the model shrinks them toward zero. This creates stability. Some approaches gradually reduce influence across all variables. Others remove weak contributors entirely. The purpose is not punishment. It is protection. By trading a small amount of bias for a large reduction in variability, models become more reliable when conditions change. Stability matters more than precision when uncertainty is unavoidable. Complexity can also be controlled by limiting sensitivity to individual observations. Some methods base predictions on similarity rather than equations. Others rely on structured decision rules that must be constrained to avoid memorization. In every case, the principle is the same. Flexibility must be balanced with restraint. Models that adapt too easily cannot generalize. They mistake historical accidents for enduring patterns. Control mechanisms are not signs of weakness. They are signs of maturity. The deeper lesson is that modeling is about trade-offs. There is no perfect level of complexity. Too little misses structure. Too much amplifies noise. The optimal point depends on purpose, data, and risk tolerance. Mathematical sophistication does not guarantee robustness. Judgment does. Models are tools. They must be shaped deliberately, or they will shape conclusions in unintended ways. Why accuracy can be misleading. Accuracy feels intuitive. If a model is often correct, it must be good. But accuracy alone can hide serious weaknesses. Some outcomes are common, others are rare. A model can appear highly accurate simply by predicting the most frequent result every time. This creates the illusion of skill without real insight. What matters is not just how often predictions are right, but how they perform when stakes are high. Blindly trusting accuracy rewards complacency and ignores asymmetry. Good evaluation begins by asking what mistakes matter most. When outcomes are uneven, evaluation must change. Predicting rare events requires different measures. Precision asks how often predicted events actually occur. Recall asks how many true events are captured. Improving one often weakens the other. Choosing between them depends on consequences. Missing a rare event may be more costly than issuing a false alarm, or the reverse. Metrics are not neutral. They encode priorities. Without understanding what a metric emphasizes, performance numbers mislead rather than inform. Evaluation also depends on how data is used. Testing a model on the same information used to build it proves nothing. Honest evaluation requires separation. One portion of data trains the model. Another helps tune decisions. A final portion remains untouched until the end. Using future information, even indirectly, contaminates results. Performance estimates become inflated. The discipline of separation protects against self-deception and reveals whether patterns persist beyond history. The deeper lesson is that performance must be interpreted, not worshipped. Strong results in one setting may vanish in another. Robust models fail gracefully rather than dramatically. Evaluation should expose fragility, not hide it. Numbers alone do not confer trust. Trust is earned through stress, variation, and humility. Models support judgment. They do not replace it. Why data preparation matters more than models. Most people assume performance comes from sophisticated models. In practice, results are driven long before modeling begins. Raw data is noisy, inconsistent, and often misleading. Errors, missing values, and structural breaks distort patterns. If these issues are ignored, even the most advanced techniques amplify mistakes. Data preparation removes friction. It aligns definitions, corrects inconsistencies, and restores comparability. This process rarely feels impressive, but it determines the ceiling of performance. Better inputs consistently outperform better algorithms. Preparation is not just cleaning, it is transformation. Choices about scale, timing, and representation change meaning. Levels behave differently than changes. Absolute values tell a different story than relative movement. Without thoughtful transformation, models learn surface behavior instead of structure. Preparation also forces assumptions into the open. How data is handled reflects beliefs about stability, relevance, and causality. Skipping this step hides judgment behind math. Careful preparation makes modeling honest rather than decorative. Feature creation is where understanding enters the process. Features are distilled representations of behavior. They capture patterns, relationships, and context. Good features simplify learning by highlighting what matters. Poor features overwhelm models with noise. Domain knowledge matters more here than technical skill. Algorithms cannot invent meaning. They only operate on what they're given. Feature design determines whether models generalize or memorize. This stage often matters more than the choice of technique. As information becomes richer, dimensionality grows. More features increase flexibility, but also risk. High-dimensional spaces make overfitting easier and generalization harder. This is why restraint returns again. Selection, regularization, and validation protect performance. Preparation is not a preliminary step. It is a foundation. Modeling builds on it, but never replaces it. When results disappoint, the cause is often upstream, not in the model itself. Turning unstructured information into signal. Not all useful information arrives neatly organized. Some of the most valuable inputs come as language, documents, transcripts, and narratives. This type of information is unstructured. It does not fit naturally into rows and columns. Before it can be analyzed, it must be translated. That translation begins by removing noise. Punctuation, formatting, and irrelevant elements obscure meaning. Cleaning does not simplify ideas. It strips away distractions so structure can emerge. Without this step, models confuse volume with insight and complexity with value. Once noise is reduced, structure must be introduced. Text is broken into smaller units, so patterns become visible. Words, phrases, and combinations carry different meaning depending on context. Some transformations reduce words to their roots. Others preserve meaning more carefully. These choices affect interpretation. Too much reduction erases nuance. Too little creates clutter. The goal is balance. Representation determines what the model can learn. Poor representation hides signal. Thoughtful representation makes learning possible. After structure comes measurement. Words must be converted into quantities. Frequency, presence, and combinations all communicate different information. These numerical representations are not meaning themselves. They are proxies. Their usefulness depends on how well they reflect underlying behavior. This is where domain knowledge matters again. Understanding what language signals in a specific setting determines whether features inform or mislead. Algorithms do not understand meaning. They detect patterns. Human judgment decides which patterns matter. As unstructured data becomes part of analysis, dimensionality grows quickly. Thousands of potential signals emerge. This increases flexibility and risk at the same time. Without restraint, models memorize phrasing instead of learning structure. Selection and regularization return as safeguards. The lesson is consistent. Information is not insight by default. Structure, judgment, and discipline turn raw input into usable signal. Without them, complexity overwhelms understanding. Why workflow matters more than algorithms. Strong results rarely come from a single clever technique. They come from sequencing. Good projects follow an order for a reason. Data is collected before it is transformed. Structure is defined before models are chosen. Evaluation is planned before results appear. When steps are skipped or reordered, problems compound silently. Weak inputs contaminate everything downstream. A powerful algorithm applied at the wrong stage cannot recover lost structure. Workflow is not bureaucracy. It is protection against hidden failure. Most effort in successful projects happens before modeling begins. Data understanding, preparation, and feature design dominate time and attention. This feels inefficient to those focused on tools, but it is where outcomes are decided. Algorithms operate within the boundaries they are given. They cannot fix missing context or flawed definitions. When projects fail, the cause is often traced back to early decisions that seem minor at the time. Workflow discipline turns scattered effort into cumulative progress. Another critical distinction in workflow is between what is learned and what is chosen. Some elements adapt automatically from data. Others define structure and must be set deliberately. Confusing these roles creates instability. When controlled choices are treated as learnable, models overreact. When learnable elements are constrained prematurely, models underperform. Clear separation improves reliability. It forces intention into design and prevents accidental complexity from driving results. As projects mature, workflow extends beyond development. Deployment introduces new risks. Data changes. Behavior adapts. Patterns decay. Monitoring becomes essential. Without it, performance erodes quietly. Strong systems anticipate change rather than react to failure. Workflow is not a checklist. It is a life cycle. Respecting that life cycle is what allows insight to persist beyond a single success. Monitoring drift and why models age. Models do not fail all at once. They decay. Environments change slowly. Incentives shift. Behavior adapts. Data that once reflected reality gradually loses relevance. This process is called drift. It rarely announces itself with obvious errors. Instead, performance erodes quietly. Decisions feel slightly less reliable. Outcomes feel harder to explain. Without monitoring, this decline is often mistaken for bad luck. In reality, assumptions are aging. Treating models as static objects ignores the fact that the world they describe is dynamic. Drift appears in different forms. Sometimes the distribution of inputs changes. What was once common becomes rare. Other times, relationships weaken or reverse. Signals that mattered lose influence. These changes can occur even when averages appear stable. Monitoring must look beyond surface metrics. It must ask whether structure still holds. Waiting for dramatic failure is costly. Early detection allows adjustment before trust is lost. Monitoring is not about perfection. It is about awareness. When drift is detected, response matters. Some models require retraining. Others require redesign. Occasionally, the underlying problem has changed entirely. Blindly updating without understanding creates churn rather than improvement. Monitoring should inform judgment, not automate reaction. The goal is not to chase performance. It is to preserve relevance. Models should be allowed to evolve, but not without intention. Change without direction is just noise. The deeper lesson is humility. No model is permanent. Success does not imply durability. Treating systems as living requires documentation, review, and accountability. Understanding why a model exists matters as much as how it works. Monitoring connects past decisions to present outcomes. Without it, confidence fades silently. With it, models remain useful long after their initial success. Judgment, responsibility, and the limits of models. No matter how advanced a model becomes, judgment never disappears. Every model reflects choices made by people. What data to include, what to exclude, what outcome to prioritize. These decisions shape results long before any computation occurs. Automation can scale decisions, but it cannot remove responsibility. When outcomes affect capital, behavior, or risk, accountability remains human. Treating models as neutral objects hides the values embedded within them. Good analysis makes those values explicit rather than pretending they do not exist. Transparency is what allows models to be used responsibly. Users must understand what a model can and cannot do. Confidence without clarity invites misuse. Opaque systems may perform well, but they create fragility when conditions change. When logic is hidden, errors are harder to diagnose, and trust erodes quickly. Transparency does not mean simplicity. It means traceability. Being able to explain assumptions, limits, and trade-offs protects decision-makers from false certainty and overreach. Ethics enter modeling through consequences, not intentions. A system can be technically correct and still cause harm. Incentives matter. Feedback loops matter. Ignoring downstream effects creates risk that math alone cannot detect. Responsible use requires asking who benefits, who bears cost, and how errors propagate. These questions are not technical. They are structural. Models influence behavior simply by existing. Awareness of that influence is part of design, not an afterthought. The final limit of any model is context. No system understands the world fully. Models simplify so humans can reason. They're lenses, not oracles. Used well, they sharpen thinking and reduce noise. Used poorly, they replace judgment with confidence. The difference lies entirely in interpretation. Models should inform decisions, not dictate them. Wisdom begins where computation ends.